Hello students, we are back to the study of the basics of the fermentation process. So as we've discussed earlier, I've taught you about the basics like how a fermenter works, then what is the fermentation medium, the crude media formulations. I think you have gone through those videos. Okay, today we will be discussing about the role of temperature. So we all know that temperature is a very important factor for growth of microorganisms as a basic study. Okay, so in the bioreactor, which is giving a space for the growth of the desirable microorganisms, one should always take care about the temperature. We all know that there's going to be generation of heat during any growth phases, like whenever an organism uses the food, it will metabolize it and gives out energy, because all the energy is not used. We all know that there's a free energy which is going to be generated, and some amount of energy is used for the work, and remaining is lost in the form of heat. Okay, I mean to say the enthalpy. Okay, so like that we understand every cell has a process. It undergoes the mechanism of catabolism and gives energy, but energy is not only for its functions but also lost as heat. Thus in a bioreactor also we can expect thousands of millions of microbes growing, and they all are going to generate heat. Imagine what's going to happen if temperature is going to be increased in the fermentation process. The cells which are present in the inoculum will be affected, the product will be affected, right? So one of the important criteria for a better enhancement of the product, one should monitor the temperature. Thus we are talking about temperature regulation. How to monitor the temperature which is developing in the fermenter. Today we have all modern equipments, like we have computerized system of monitoring, where I'll be talking about that topic in future one class. Okay, how oxygen levels, pH levels, etc. are going to be monitored computerized methodology. But today we will also learn little about how we are monitoring, how a fermentation process is monitored with simple methodologies, like and how to regulate it, how we can bring, what is the action plan taken when temperature is increasing. At home also we can understand these processes. Whenever you have a fermentation process like your idli batter preparation at home, you observe properly, there's a heat generated. Okay, so heat is something which is going to happen as a natural process, so one cannot avoid this. Only thing is, we have to understand how the fermentation industry will be involving themselves in producing, enhancing the end product. Okay, whatever they want to harvest, they always think about a betterment in that, right? So imagine alcohol production, what's going to happen if alcohol is the product which is going to be produced by yeast in the fermenter, and we are going to recover the alcohol. So we should be extremely careful about the yield. Otherwise, what will happen if temperature increases? There is going to be vaporization, and recovery will be definitely going to be reduced. Okay, so in every fermentation process, we have to follow, we have to understand the temperature is important. And today we will be learning about the factors also. What's going to happen for the cells, and mainly the aeration. Aeration also will be affected. Okay, I'll be talking little about aeration part along with this. Let's see the coming videos. We will be looking into those aspects also. So for today's topic, the lesson what we'll be learning is what is temperature regulation, how temperature is detected and regulated in the fermentation process in the bioreactor. So students, I have a few points, please go through them. Okay, so here you are seeing that the fermentation process brings a lot of heat, right? I was telling you about that. Please highlight that point. And due to metabolic reactions, the lost heat changes the temperature in the medium. What is lost heat? That's what is enthalpy. So any cell which is going to bring about metabolism will definitely produce heat, and that is going to affect the system, okay, of fermentation process. So here growth of the inoculum cells is very important. It reduces the rate of product recovery. Already I told you this in the introduction. Okay, as we go ahead, you can see that the temperature of the medium can be detected by using some temperature monitoring probe. Please make a note of this, temperature monitoring probe. What is temperature monitoring probe? It's a detector. It's a system which will going to help us in identifying the mechanism of how to detect the temperature. I have some diagrams as I go ahead. Okay, the different types of temperature monitoring devices. One of them is called as the thermostable bimetal. Okay, there are some strips of two or more metals which are fastened or bound close together. So you can see in this diagram, two bimetal probes are, what is a probe? Probe is a detector. Okay, so you can see two metals which are small strips of metals which are present. Okay, usually in the fermenters, what they will do is, in this region there will be some glass viewers in the old fermenters and all, traditional fermenters, exactly at this point, like a box, imagine like a box, there's a glass viewer where the bimetal will stand. Okay, exactly at that point one can see and identify. What they will see and identify? See this picture here, what will they identify? Deflection of the metal indicator, changes in media temperature. So whatever the temperature has changed in the medium, automatically the bimetal is going to be showing some difference. I'll come back here. What do you see here? They are close by. And what do you see here? They are deflected. So metals will get deflected. Metals will get deflected. The metals are usually made up of certain materials which are very sensitive to heat.
Duralumin.
Duralumin is one of the metals which is used. Duralumin is a very sensitive metal which can be light in weight also. It won't be affecting the fermentation process. It can be used. Of course, gold and silver can also be used, but they are all very expensive. There are other models what you're seeing here. Can you observe the other models here? What do you see here? One is a straight wire and the other is a coiled wire next to it. Another way of detecting. In the same bimetal, replacement is this. As temperature increases, what's going to happen? The wires are deflected. The one which is the coiled is deflected. You can see the difference between the two. So the sensitivity of the metals is for the high temperature. Similarly, multiple metals can be used here. You can see as heat is generated, they get deflected. Okay, these are the ways of identifying. Okay, so this is one of the methodologies. Coming to pyrometers. What is pyrometer? Pyrometer is called radiation pyrometer. Okay, as temperature increases in the medium, the radiated heat is detected and recorded in a pyrometer. So these are instruments which are used in the detection. So what is the next one? What you are seeing? Glass bulbs were used as a probes. Okay, so what is the meaning of this? In the bulb, they would fill certain materials like mercury or alcohol. Okay, so each one will have its own sensitivity in temperature. As the heat is generated in the fermentation process, inside the glass bulbs, the color changes will happen. Okay, so they'll be having a specific what do you say, temperature above which it will show some changes. They'll mix some dyes in that. Okay, the dyes will change in the bulbs. Color, whatever dyes you've added in the bulbs, the dyes will show some color changes according to the temperature. Okay, so one can understand that there can be certain technologies which are there, very simple methodologies where one can detect the temperature by using the bulbs. What do you see here? It's a strain gauge. Strain gauge is a wire which is heat sensitive with electrical conductors. Okay, what happens is as the wire is very sensitive, as there is going to be heat generated, the wires will start stretching out and increase in the length. So any layman need not, like earlier days they were not much of they were only trained personnels in the fermentation industries. They will be just monitoring these aspects. They'll see, okay, there is something wrong. They'll have a standard length of the wire. It has got increased. There are some measuring devices here. Externally in the fermenter and the glass viewer, it will be there. So the increase in the length can easily tell there's something wrong. It can be easily detected. Okay, it can be used to even measure the pressure in the medium. We can see if there is pressure, also strain will be increasing in the fermenter, strain will be developed. Stress will be developed due to pressure. When that is going to affect the cells, that also can be understood by this mechanism. Okay, so strain gauge is another thing. So there are different ways of detecting the temperature like this. to add on, what is the action, corrective action taken? How can we understand that once we understood this temperature has increased, we have to regulate it. We have to bring a regulation process. So it can be done by a manual process. Earlier manual process only was done. So you have cooling jackets here in this, you can see there's a entry of the water, there's a jacket outside the bioreactor, it's only a cross section. Imagine completely covered with the jacket on all the sides, it will be like a bowl. Okay, that once water is entering, it will automatically cool the medium. Okay, and thus one can understand, one can regulate the temperature in the bioreactor. Some and few other modified methods were the cooling coils. Okay, in the fermenter wall itself, you have a coil running. You allow cool water to pass, and as the water is entering the coil and it's running out, the medium inside will get cooled. Cooled in the sense it should be brought down. Temperature should be brought down. Of course, not below the undesirable temperature. Okay, so that needs again a monitoring. Water is passed in the cooling coiled pipes running inside the wall of the fermenter, and then temperature is regulated, as I told you. So there should be monitors for all the things. And more modified nowadays is these all are actually, can you tell me what's the demerits in these above methodologies? The pipes might get worn out over a period of time. There can be a contamination unexpectedly. Okay, so no one will take the risk generally. Okay, so in that context only they brought another simple methodologies like designing the bioreactors in such a manner. Can you see the type of bioreactor here? Large head space. What do you think about this head space which is larger here? It cools the medium automatically. Okay, so whenever as a media, I'm not showing the agitators impellers here, just only the design I've tried to show here. Okay, so you can see that there's a large surface area. The designing of the bioreactor is such a way that the large surface area brought in. When you see a large surface area brought in because of the spheroconical, I think we can call them spheroconical bioreactors. Lot number of bioreactors have been designed according to the requirements. If a question is asked on bioreactors and its types, don't just stick on to the bioreactors what you're learning in the syllabus. Don't write only those. You classify as batch and continuous. I'll be talking about the bioreactors separately. I think you have one topic on this in the other chapter. Okay, anyway. So bioreactors are this is a batch fermenter. Continuous fermenters are different. It's a cascade. Cascade means 3 or 10 bioreactors connected together. Anyway, this is only a single one what I've tried to show. This is only a batch bioreactor where you have large head space. Whenever the media is rotating, I'm not shown agitators, I told you. So as it's rotating, what will happen? It just cools because of the air, the large surface area which is there above this. What is this called? Head space. So more head space is the major criteria in this particular, spheroconical types of bioreactors. Why? Why we should design such thing? To cool the medium. It cools the medium, and thus it's a very well equipped, easy, simple methodologies. These all are designs which are done according to the requirement. So we cannot explore it. Every industry has its own. Whatever books give you is only a model. If you go and visit, you will understand the differences. So every industry, it's a trade secret. Every industry will have its own bioreactor, its own way of thinking. I think with that general idea, you would have understood what I mean to say. Okay, automated cooling systems are also there. Computerized software which helps in running the cold water in the coils. Automatically it will happen. No need of manual. I was telling one person should open the valve for the jacket and then it should cool. No, that's different. Now we can follow this automated system. Okay, that's another way of a very renowned and well-developed methodology of monitoring system. Not only for temperature, it can be automated for the pH, automated for the transfer of oxygen, all those things. Okay, I'll be continuing with this topic little about the oxygen transfers also. Okay, yeah. Children, what do you see in this picture? You see a bioreactor, you see the main agitator. Already I've shown you this picture somewhere. Okay, so here there's a sparger which is going to give the aeration bubbles. This is a sparger. I'll be talking about sparger a little more later. Okay, spargers which gives rise to the air bubbles. So this is the air bubbles which are formed. So what is your topic in this? I've just shown a picture here. Don't think it's a sterilization topic. This topic is about aeration. So through polytetrafluoroethane filters, the air is coming inside and is escaping into the medium. Okay, so according to Pascal's law, you can find that whenever there is a entry of air, okay, in a enclosed vessel, they move in all directions. That's what happens here. Bubbles, once they escape from here, they start moving in all directions. But the impeller blades will do its work by rotating them. Some of them don't have impeller blades. No, they are just moving in all the directions. Okay, so keep this in mind while reading about a bioreactor. So here you are seeing that bubble is going to be distributed in all directions, right? So this is only to tell you that the aeration is a very important starting point of how it's donated or how it's released into the bioreactor. Now we should follow how it is used. Okay, we'll be learning that. Okay, here are some data of how much oxygen should be given. To supply sufficient oxygen without damaging the cells is a very important objective. Why? Because we should give oxygen and it should not, the bubbles whatever is released inside is going to give the oxygen. Air bubble whatever is entering inside this is not only oxygen, few other gases. It's not only pure oxygen which is given. Only in the animal cell bioreactor they'll give pure oxygen. But here in a normal fermentation industry like alcohol productions and all, they will, and antibiotics etc., they don't need to give pure oxygen. Okay, yeah, please keep that in mind. The supply of the air is given. Sterile air, of course, sterile air bubbles. Got it? So this is what I was telling you. In the sterile air bubbles are given in the bioreactor. Sterile air bubbles. Okay. So how much of oxygen rate should be there? Like, mean oxygen utilization rate by cells is 6 milligrams per oxygen for 106 cells per hour. This is data. Please remember, oxygen is sparingly soluble, not very easily soluble. Sparingly soluble in water, in culture medium. Culture medium will have water. Keep that in mind. So that means diffusion is very slow. That is why we call oxygen transfer rate. Please remember, oxygen transfer rate. A cell, when it is getting the oxygen from the bubble, is not so easy. Okay? Yeah. It has to pass from the from its gas phase to liquid phase. 16 micrograms of oxygen is going to be diffusing per centimeter per hour. It's very less oxygen diffusion. That's why it will take its own time for fermentation. And it's also good because the cell will not use all the oxygen at the same time. No. It's so much matching. The cell growth, the cell division matches with the oxygen transfer rate. That is God's boon. Okay. How much oxygen is going to diffuse into the medium is less. How much is going to use is again going to be less because it has to divide. It will take its own time. By the time oxygen transfer rate will balance with the cell division rate. Okay. Yeah. Please, with that context, you understand it. Sufficient aeration can support only 50 into 106 cells in 1 liter culture flask. These are standards. Okay. Efficient aeration is achieved by what? Bubbling air into the medium. That all of you know. Okay. 7th point tells what? Damage to cells can be reduced by making large bubbles. Very important. Make a note of that. Large bubbles. Low gassing rate. That means what? It's both are synchronizing. You should not give more of gassing rate inside the fermenter. Okay. There should be low pressure. The time large bubbles are formed. When you give high pressure, small bubbles are formed. What is the use of the large bubble? More larger the bubble, more the oxygen on the surface. I'm just drawing, just to understand. Larger the bubble, on the surface of the bubble you will find oxygen. Keep that in mind. Okay. And by addition of non-nutritional supplements. Okay. So we can use pluronic F68. This is not a nutrition. Okay, we can prevent damage of the cells by using such things. What is shear force? Damage. Okay, damage of cells. Can use sodium carboxymethylcellulose. You can be thinking why I'm telling you this here. It's all interrelated. In the medium, this is added. Keep a note of that. That's all. Okay, it's not very directly related to the oxygen, but we can understand, that's all. Silicon tubing, highly gas permeable one. Silicon tubing is done in certain bioreactors. That's only for animal cell cultivation. We use that. Animal cell cultivation. We use silicon tubing, high gas permeable. There they have to give 2 to 5 centimeter in 1000 liter flask. That's only for animal cell cultivation where pure oxygen should be given. We should not think about other methodologies in that case. No air, it is oxygen. Oxygen bubbles. Please make a note. Air bubble, oxygen bubble. Little of difference is there. Air bubble is just gases. Oxygen bubble is only oxygen. Okay. Yeah. Methods, the different types of methods, I'll not go to that much detail because we all know that the porous sparger, orifice spargers and all that is different types of spargers. I'll discuss that later on. Okay. In today's class, we will understand a little more about oxygen transfer. As I told you, there's a very good picture here. Of course, I cannot. It's a picture which is going to be descriptive. This is a bubble. On the surface of the bubble, you have oxygen. Okay, oxygen is sparingly soluble, and since it has a low surface tension, you can expect oxygen is present on the surface of the air bubble. Now, what is the work of this oxygen? Now, it should diffuse from this gas bubble phase into liquid. Imagine this is a liquid medium here. I'll give you a picture for that. So here, imagine there's a liquid phase. It should come from the gaseous phase to liquid phase. It is sparingly soluble. Keep this in mind. Okay. It is transferred into the medium and used by the inoculum cells. Please note down this picture. What do you see in this picture? The same gas bubble is there here. Oxygen is on the surface. This is the gas fluid interface, pure fluid. And again, you have the similar fluid which is near the cell. So it has to go from here to this. So 2 phases, it has to mainly pass from here to here. 2 phases are there. Okay. That's what we are trying to understand in this picture. So what do you see? We can understand this in different phases. So let me explain that first. See this graphical representation. Imagine this is gas bubble. Can you synchronize it? Gas bubble, gas film, fluid film. These two are shown here. This is what is shown together here in the green color. Here the same. Gas film, fluid film. Pure fluid, again fluid film close to cell. And this is the boundary of the cell. Fluid film cell phase. This is cell. Where is the cell?